One neat thing about Stokes' theorem is the thing that also is like the hardest thing about it. So when we do Stokes' theorem problems, we have this issue where we have to pick the particular surface we're going to think about, whether it's the bendy surface or the flat disk surface or something else. But because of that, we can actually use Stokes' theorem to not just convert line integrals into surface integrals, but to use it to convert between two different surfaces that share the same line integral. And so we're going to do an example that kind of does that in a fun way now. So we're going to try to evaluate the surface integral of the curl of the function f equal to x y squared z e to the xy over s, the outward oriented portion of z equal 1 minus x squared minus y squared above z equals 0, or above the xy plane. And so what this is telling us is that we're looking at z equal 1 minus x squared minus y squared. That's our good friend, the bowl. It's oriented outwards. And we're computing the flux of the curl of f over this surface. And so you could go ahead and set this up kind of manually. You could say, okay, here's my del cross f. Here's my I hat, j hat, k hat, d dx, x, d dy, y squared, d dz, e to the xy. And that's going to give me I hat times d dy, e to the xy. It gives me e to the xy times x minus d dz of y squared gives me 0 plus j hat. Oops. Made that mistake I always tell y'all not to make. Minus j hat times d dx of e to the xy. That gives me y e to the xy. Minus d dz of x gives me minus 0. Plus k hat times d dx of y squared gives me 0. Minus d dy of x gives me 0. So that normal vector is x e to the xy minus y e to the xy, 0. And if I wanted to set up this surface integral problem as written, I would have to write my f equals 1 minus x squared minus y squared, compute my n, compute my ds, plug everything in, find my region, and then integrate it. Instead of doing all that, I'm going to say I'm finding a surface integral of a curl corresponding to this curve. So just like I could compute that curve, that curve's line integral using a surface integral from Stokes' theorem, I could go ahead and convert that surface integral into a line integral using Stokes' theorem. Usually don't want to do that because it's usually harder. And I could parameterize that curve and calculate this whole thing. But I can take it one step further. And I can say, once I'm thinking about that line integral, I could go ahead and convert this to being a surface integral over an entirely different surface of del cross f dotted with n ds. So instead of that bowl shape somebody gave me to work with before, I can say, I know there's a ring around the bowl that forms a closed curve, and I know that there's a circle inside that ring that would form a surface that's equivalent to that line integral. So it's the same as the thing I was asked to do to start. Sweetie, stop stepping on my computer. But the reason why I would want to do this whole like circular argument is because S2, the purple thing I just shaded in, is flat. It's this thing. It has normal vector 0, 0, 1. If n equals 0, 0, 1, then I could go ahead and write my surface integral. Oops. Del cross f dotted with n ds as surface integral of, I think it was y e to the minus xy, x e to the minus xy. Flipped that around, sorry. It doesn't matter, but I want to make sure I get it right. X e to the xy, y e to the xy, 0, dotted with 0, 0, 1 ds. I'm not going to worry about setting up my bounds of integration because when I take that dot product, I'm going to get 0, 0 times x e to the xy plus 0 times y e to the xy plus 0 times 1. And so this integral that I was asked to compute is just 0. It would take me much longer to recognize that by plugging in the problem as it was given. So converting to flat surfaces when you recognize this fact can save you time. Even if it doesn't save so much time as making the integral 0, it could have made this inside a constant, and then you're just finding an area of a circle like it was for previous example related to Green's theorem. So this is kind of a good trick to have in the back of your mind whenever you are asked to evaluate a surface integral of a curl of a vector field, because usually there's an easier way to do it.